Okay. We're probably not going to get through all of 9.3 today, but we'll get through the majority of it so you can at least have a sense for what's going on here. This section is on geometric sequences and series. So we talked about the difference between arithmetic and geometric, but let's just go through and kind of summarize and make sure we're all clear on this. Okay, so we're going to have formulas that we need to know and be aware of for both arithmetic and geometric sequences and series. If you understand how these sequences and series are put together, it kind of reduces the need for memorization. I mean, you just kind of understand it and get what's going on. Okay, so our goal here is to make sure that you understand the process, because from what I understand on the state testing that they're going to do, they're going to kind of try and see whether you can think mathematically and figure stuff out. And that's why it's important to be able to do stuff like this. So again, just for review, an arithmetic sequence or arithmetic sequences have common differences between every pair of terms. And the way we go from one term to the next term is we always just add whatever the common difference is to get to the next one. Okay, that was kind of the recursive type of definition, which we'll look at again here in just a second. Okay, so that means that the nth term formula for an arithmetic sequence is, and we had this phrase right here, if you can fill that in, then you'll remember what the formula is. We take the first term and we add n minus 1 common differences. And that's why the formula looks the way it does. Here's the nth term. We get to the nth term by taking the first term, and again, sometimes they'll put a subscript of 1 there to indicate it's the first term. If not, it will just be an a, and that means it's the first term, plus n minus 1 common differences. Well, if you think about it, the only difference between an arithmetic sequence and a geometric sequence is, instead of having a common difference, they had a common, anybody remember what we called it? A common ratio. And instead of adding to go from one term to the next term, what did we do? We multiplied, okay? So they have a common ratio between every pair of terms, and we multiply by the common ratio to get from one term to the next term. So that means that the setup for this should be exactly the same. The phrase that we can use to remember how these sequences work is almost identical. So it says the first term, in order to get the nth term, we're going to take the first term and we're going to not add, but we're going to times by n minus 1 common ratios. So up here we had the first term plus n minus 1 common differences. Here we're going to have the first term, so I'm going to write a sub 1 times n minus 1 common ratios. And that n minus 1 has to go up in the exponent. So you'll have some problems that are pretty darn easy. You just need to look at them and be able to determine what maybe the first term is, what the common ratio is, come up with a formula and that sort of thing. So we've got the sequence right here, and we want to find the common ratio. To find the common ratio, you take any term and divide it by the one before it. So if I take 4 and divide it by 8, I get 1/2. If I take 1 and divide it by 2, I get 1/2. And if I take 1/2 and divide it by 1, I get 1/2. So every one of these pairs of terms, if I take the next term and divide it by the one before it, I always get a ratio of 1/2. And that's what we mean by having a common ratio. Okay? So the recursive definition for an arithmetic or a geometric sequence or series can be very useful. Okay, so remember, we're going to find the common ratio. Whoops, I have a typo right there. The ratio by taking any term and dividing it by the term before it. So this is what I was talking about. This is the term we're on. This is the one before it. That's the term we're on. That's the one before it. So if I take that right here, we can actually write this down as a recursive definition. If I just solve this for a sub n, the way I solve for a sub n is I times both sides by a sub n minus 1. So this is going to be a sub n minus 1. And again, you've got to get used to how those indices work. You've got to make sure that you keep that straight. whatever number I plug in here, so if I plugged a 10 in here, this would be the 10th term. This would be the 10 minus 1 term, or in other words, the 9th term. So the way you get the 10th term is you take the 9th term and you multiply it by the common ratio. Okay, or I said this is the next term and this is the one right before it. That's what that minus 1 means. Okay? Any questions there? Okay, what if I wrote this? A sub n plus 1 equals r times a sub n. What does this mean? This would be the next term, right? And what would this be? The current term. Okay? So notice that this is one ahead of this one right here. So that's the next term in line. That's the one we're on. Notice how this one right here is, or we'll go this way. This is one before that. So take the one before it times by the common ratio to get the next one, or the one we're on, if you want to think of it that way. Okay? So it's important to understand how those indices work. Okay? The instructions for this one say write out the first 4 terms of the geometric sequence and find the common ratio. So we don't have to wonder like we did about a week ago, well, what number do we start by plugging in? We're always going to plug in a 1. So the first term is 2 to the first, so that's 2. The next term we'd get when we plug in a 2, so this is going to be a 4. Plug in a 3, so that's going to be an 8. Plug in a 4, so that's going to be a 16, and so forth. It continues on like that. There's our pattern. We've produced the first 4. And then we just need to figure out what the common ratio is. Take any pair of terms, divide this one by the one right before it. So if I do 16 divided by 8, I get a ratio of 2. If I do 4 divided by 2, I get a ratio of 2. So the common ratio on this one is 2. If I do this one, plug in a 1, I get a 2/3. Plug in a 2, I get a 4/9. Plug in a 3, I get 8/27. Plug in a 4, I get 16/81. And again, that pattern would continue, but we only have to find the first 4. So let's find the common ratio. Take any pair of terms, and I'm going to blow this up so I've got enough room to write this. Take any pair of terms, divide the next one by the one before it. So I'm going to do 16/81 divided by 8/27. Complex fraction. We never divide fractions. I'm going to flip this one over and I'm going to multiply. So I'm going to multiply by 27/8. I'm going to cancel the 8 with the 16. That's going to be a 2 on the top. I'm going to cancel the 27 with the 81. That's going to be a 3 on the bottom. And there's the ratio between those two terms. Just to double check, I mean, you ought to do more than one pair of terms. So I'm going to take the 4/9 and I'm going to divide it by 2/3. Again, I'll cross this one off. 3 on the top, 2 on the bottom. Cancel there, that's a 3. Cancel there, that's a 2. So I end up with a ratio of 2/3. Okay? So there's my common ratio for that particular one. And what we want to notice is, can you see on here anything about the formula or the type of function we're dealing with that produces a geometric sequence? Like the ones we did before, the arithmetic ones, they were kind of linear. They were just like 7x or 7n. Or negative 3n plus 7 or something like that. Okay, they were very linear. What do these look like? They're exponentials. Very good, Hop. Okay, so those are exponentials. Okay? So one thing you want to look at is, are the terms getting bigger or are they getting smaller? On this one, clearly they're getting bigger. How about on this one? They're getting smaller. Okay? So if I have a ratio that's bigger than 1, they're going to get bigger. And if I have a ratio that's smaller than 1, even if it's just a little bit smaller than 1, like 9/10, it's still going to get smaller and smaller and smaller. Okay? So it depends on whatever the base is. If the base is bigger than 1, it gets bigger. If it's smaller than 1, it gets smaller. Okay? Any questions? We're talking in absolute value there. Okay, I do want to show you one more thing that's kind of interesting, and it's a good exercise in working with exponents. So you can actually use that formula right here take the nth one and divide it by the one before it. Now this is going to look a little bit strange. If I do 2 to the n and I divide it by 2 to the n minus 1. Now we don't often work with stuff like this, okay, but here's what I'm going to do. If we have the same base on the top and the bottom when we're doing division, we subtract the bottom exponent from the top. So that's going to be, that's going to be n minus 1, which is n minus n plus 1. These cancel each other out, so we end up with a 2. That right there is the ratio. Now, that's, in some sense, I mean, it's maybe a little bit shorter than what we did right here. It certainly was shorter to talk about, okay? But seems a little bit strange. Why wouldn't you just write out a couple of terms and go ahead and do the division, or recognize that it's an exponential and the base is 2, so that's going to be the common ratio. This idea right here is going to be very helpful in about 2 years because you're going to be taking calculus, okay? So this idea that you can take these and manipulate them, go ahead and do this ratio right here and see what we end up with, is a good skill. So let's just double check and make sure that it works on this one. This would be, 2/3 to the n over 2/3 to the n minus 1. I'm going to do this one just a little bit differently. 2/3 to the n. I'm going to write this as 2/3 to the n and 2/3 to the negative 1. Isn't that okay to write it like that? And then I cancel that off with that. So I have a 1 on the top and a 2/3 to the negative 1. I can move that up in the exponent, or up in the numerator, and that just becomes 2/3. Okay? Negative exponent in the denominator, take that entire factor, move it up in the numerator, it'll change the sign of the exponent. Okay, any questions? Okay. You're going to have some problems that'll say, hey, look at this and figure out whether it's arithmetic or geometric. Okay, maybe not a ton in this section, but definitely by the time we take the test. So look at these and figure out, are they arithmetic or are they geometric? If they're neither, you don't have to worry about it. There are some on here that are neither. If it's arithmetic, I want you to find the common difference. If it's geometric, find the common ratio. And then what I'd like you to do is graph the sequence on the coordinate plane, if it's arithmetic or if it's geometric. And let's take a look at how these grow. So on this one, what I'm going to do, again, we're going to plug in a 1. If I plug in a 1, what's the first number in the sequence? It's a 1. Next one? It's a 3. Then a 5. Then a 7. Okay? So these are the counting number, or the odd numbers. So if I plug in a 1, 2, 3, 4, I get a 1, I get a 3, I get a 5, and I get a 7. Notice how they make a nice linear pattern there? Arithmetic. Common difference? 2. Remember, we talked about how you can look at the formula. This is a linear pattern, and how do you know what the common difference is? Just by looking at it. Whatever the coefficient is, or in other words, whatever the slope of the line would be. It's right there. Okay? So a linear function right here produces an arithmetic sequence, and the common difference is whatever the slope is, or whatever the coefficient on the variable is. Everybody good there? Okay, take a look at the next one. Plug in a 1, we get a 5. Plug in a 2. No. Remember, the exponent only applies to what it's over. If we wanted it to apply to the 4, we'd have to put it in parentheses. What's that? No, because if you plug in a 2, okay, so plug in a 2, we're going to end up with, let's see, that's 17. Okay, so if we stopped right here, we've got a common difference of 12 or a common ratio of 17/5, right? Okay, but a couple of terms is not good enough, so let's plug in a 3. I get 30, 37, okay? The difference between the two of these is 12, and the difference between the two of these is 20. No way this is arithmetic. Not possible. And if I take 17 and put it over 5 and 37 and put it over 17, are those two equal? They're not. Okay? So this is not arithmetic or geometric. Now, does that mean it's not a sequence? No, we can have all sorts of funky sequences. Arithmetic and geometric are just two special categories that come up a lot, so we study them. Okay, they have some really nice properties. Okay, so we don't have to do anything with that. Notice that this one over here was linear. If we had to say what this was as far as a function goes, what type of function is that? Okay, so if we graphed it, it looks like a parabola. Okay, what's the fancy name for it? It starts with a Q? Quadratic. Okay, so a quadratic function does not make a geometric or an arithmetic sequence. Okay, linear is going to be arithmetic, exponential is going to be geometric. Okay, this one doesn't give us a formula, but let's take a look at it. We've got 1, then 3, then 6, then 10. Okay, the difference is 2 right here. The difference is 3 right here. We can stop right there, not arithmetic. Is it geometric? It's not geometric either. 3 over 1 makes a 3. 6 over 3 makes a 2. It's not arithmetic or geometric. Okay? Don't have a formula, but we can spot through the pattern by checking the differences and the ratios to see whether or not it's arithmetic or geometric. Okay, let's take a look at this next one right here. Arithmetic or geometric just by looking at it. Okay, got to be geometric. Why? Because it's exponential, right? So if you plug in a 1, you get a 1/4. If you plug in a 2, you get a 1/16. Then you get a 1/64th, and then you get a 1/256th. Correct me if I'm wrong there. Is that right? So if we were to graph this, here's what it would look like. Here's 1, here's 2, here's 3, here's 4. Okay? I'm going to put 1 way up here. So 1/4 is about right there. Then it's 1/16th. Tiny little thing right here. Then 1/64th. Barely above the x-axis. And then for all intents and purposes, at least for what we can graph as far as accuracy goes on this paper, okay, 256 is just barely above the x-axis. And what's going to continue happening as we plug in larger and larger numbers? Smaller and smaller and smaller. How small is it going to get? Infinitely small. Is it ever actually going to equal 0? No, but it's going to get really, really close to 0. In fact, we say that its limit is 0. If you just did that forever, okay, it would get as close as you can possibly get to 0 without actually equaling 0. Okay? So we call that a limit. Okay, any questions there? Anyway, this one is arithmetic? Nope, because what's the difference between the first two? 0. And then we've clearly got a difference that's not 0 between these others. So this is not arithmetic. What about geometric? Ratio here would be 1. 1 over 1 is 1. And all we have to do is step to the next one. 2 divided by 1 is 2. Doesn't have a common ratio. All you need to do is find one common difference, or one difference that's not the same, or one ratio that's not the same. End of story. It's not arithmetic or geometric. Okay, any questions? Okay, how about this one? It is geometric. Okay, it is geometric. Okay, it fits the technical definition for a geometric sequence, because if I plug in a 1, I get a -1, then a +1, then a -1, then a +1, and so forth. Okay, So this is, whoops, geometric, and the common ratio on this one is -1. Notice that it's the same as the base of the exponential. Okay? Now, if I go through and I graph this, 1, 2, 3, 4. First one's -1, then +1, then -1, then +1. Does that look like an exponential function? Remember, exponential functions normally do this. They normally grow exponentially or decay exponentially. Doesn't look like either one of them, so it's one of those oddballs, okay? -1 to the n, we use that if we want to make a series or a sequence alternate, okay? And what about this one right here? What if I did, whoops, what if I did +1 to the n? Does that qualify as geometric? Yeah. It's pretty darn boring though, because what is it every single time? It's 1. Okay? And frankly, does that meet the definition for an arithmetic one? What's the common difference? Common difference would be 0. Okay? So you get a couple of oddball ones. You want to be careful about those. Okay? They are useful. In fact, we use that alternating one quite a bit. Okay? All right. Any questions? Okay. We're going to try and finish this first page if we can, and then I'll let you go. Just kind of let that sink in. Before you leave, I do want to see 9.2. Okay? I'll have you turn that in before you leave here. But it says, for these problems right here for A, B, and C, find the nth term and the 8th term. Find the nth term and the 8th term. So, don't look up at the top of the page. I want you to think for just a second, because I'm hoping that you can have the ideas understood, and then you don't have to memorize this. The way we get from the first term to the nth term is we multiply it by n-1 common ratios. So the formula is the nth one is going to be, whoops, make it a little bigger and maybe that gives up on me here. Okay. Good, that's going to stick around. The nth one is going to be the first one times n-1 common ratio. So if you know the first term in the common ratio, just like with the arithmetic one, end of story, we know the formula. So the nth one is going to be 5 times 2 to the n-1. So this formula right here is the nth term formula. And if you want the 8th one, you take the first one and you multiply it by how many common ratios? 7. Plug an 8 in here, plug an 8 in there. 8 minus 1 is 7, so 7 common ratios. So this is going to be 5 times, let's see, correct me if I'm wrong. This is 128, isn't it? Okay, so if I multiply those together, what do I get? 640. There's the 8th term. Everybody good there? Okay, watch please. Okay, this textbook may or may not write these like this. I kind of like this formula better, but your textbook may write something like this. It may do this, 5 times 2 to the n times 2 to the -1, and then it treats that negative exponent so that it can make it positive. So we're going to write it this way, 5 over 2 times 2 to the n. Now, that's a perfectly good nth term formula. If you plug in an 8, you get 2 to the 8th times 5 halves. If you plug in 2 to the 8th times 5 halves, you're still going to get 640. Okay? Now, I will admit that this one right here looks better, but this one right here is easier to understand as far as the similarities between arithmetic and geometric. You take the first term, you're going to multiply, because it's geometric, not arithmetic, by the common ratio n-1 times. Instead of adding n-1 common differences, you're going to multiply by n-1 common ratios. Okay? Cleaner format. Yeah, you end up with a fraction, which isn't so nice, but at least you don't have a negative in the exponent. Okay? I prefer this one right here. I don't care which one you use. Okay, but I think this one is much easier to understand and work with in the long run. Okay, any questions? Okay, two more. Let's take a look at this one right here. What do you need to know if you're going to write down the nth term formula? Common ratio and first term. What's the first term? -3. All we need to do is identify the common ratio. We notice something about this. It's going from positive to negative, from positive to negative. So that means the base is going to be negative, because that's going to allow it to alternate. 1 divided by -3, -1/3. -1/3 divided by 1, -1/3. 1/9 divided by -1/3, -1/3. So the common ratio is -1/3. So here's our nth term formula. First one is -3. Ratio is -1/3 to the n minus 1. I would prefer that, but if you want to change the format, -3, -1/3 to the n, -1/3 to the -1. So that would be -3. If I flip this over, that's also a -3, and that's -1/3 to the n. So the other way that you could write this would be +9, -1/3 to the n. Okay? Again, this is nice because it fits the format. It's fundamentally how we're getting from the first term to the nth term, and you don't have to fiddle with it as much. Okay? This looks a little bit nicer. Okay? Either one you want to use is fine. And then what is the 8th term? 1/729, and it's positive, right? Whoops, thanks. 729. How could you tell just by looking at this list that your answer for the 8th term is going to be positive? Because it's even. Yep, because it's even. Very good. Okay. Any questions? Okay, let's look at this one right here. This can be kind of hard, or we could make it relatively easy. Do you remember how we did these when these were arithmetic? We went through a little shortcut. We could set up a system of equations. We could do this. We could say the 4th term is the first one times 3 common ratios, 4 minus 1. We could say the 10th one is the first one times, how many common ratios would it take to get from the first one to the 10th one? 9 common ratios. So that would mean 91 is equal to a r to the 3rd. That would mean 91/64 is a r to the 9th. And then we could solve that system of equations. Looks like a bit of a pain in the butt, doesn't it? How many common ratios are there between the 4th term and the 10th term? Aren't there 6 common ratios? Wouldn't there be 6 common ratios? Okay. So that would be r to the 6th. Now, do I subtract these? You divide. Okay? And if you want to notice, if I did 10 minus 4 to get the 6th, I'm going to do this divided by that. So I'm going to get 91/64 divided by 91. Make that a fraction. Flip that over. Cancel this off. This is 1/64. Everybody good with that? Okay. I want you to watch so you fundamentally understand what's going on here. Does everybody understand that this is the 4th term? This is the 10th term? So watch how I can make this using these guys right here. What would happen if I divided by 91 a r to the 3rd? A's would cancel. 3 of these would cancel with 3 of those. I'd end up with a 6. So don't I end up with r to the 6th? 91/64 divided by 91. Don't I end up with exactly the same thing? How do I solve for what r is? Sixth root. So I'm going to take the sixth root here and the sixth root here, and lo and behold, it's a nice number. The ratio is 1/2. Now, you're not done, but you're most of the way there. What do you need in order to make the formula for the sequence? First term and common ratio. We've got the first term. Sorry, we've got the common ratio. I need to plug it into one of these in order to figure out what the first term is. So I'm going to plug that in right here. So this is going to be 91 equals a times 1/2 to the third. And let's see, is that 728? Is that what it is? $728? Okay, so this is 91a, this is 1/8. So I multiply both sides by 8. So a is equal to 728. So our formula is 728, 1/2 to the n minus 1. And then I'll leave it for you to figure out what the eighth term is. Okay? Okay. 9-2 up here. If you're done with it. If you're not, keep it. Turn it in like tomorrow. And so I've put the videos. There were a couple days where I didn't upload the videos. I've put the videos up there for 9-1 through 9-2. I've also put the homework up on the website up through 9-3. And by tomorrow, I'm going to hopefully have everything up through the end of the chapter as far as homework goes. Yeah. Did we not turn in 9-1? I thought we turned it in. Okay. You just make sure your name's on it. Make sure it's clearly 9-1 up here, and I'll get it. Okay.
I had done that out of the way. I didn't.
All right. That's okay. Don't worry about it.